All right, well, welcome back. Just at the beginning, I wanted to clear up that, as you know, we didn't really get into the Chapter 4 study guide. So we haven't talked about ethane or butane conformations. We haven't talked about Newman projections. We have also not talked about the chair and chair conformations and so on. So that will not be on the exam. It's also, because I had hoped we would get there, I put it on the practice exam, but you don't have to do those problems of the practice exam before you take the test, and you can go ahead and report on Learning Suite that you completed practice exam 1, because we'll just move those questions to practice exam 2. Is that clear? Everybody get it? Okay. All right. So we just need to do a few more things with non-covalent interactions to finish up on Chapter 3. And so last time we had talked about ion-ion interactions. We had sort of debunked the concept of an ionic bond, at least in aqueous solution. And we had talked about the importance of talking about the strength of something as being relative to something else. We talked about how, sure, an ionic bond is strong relative to those two ions being separated at infinite distance in the gas phase. However, relative to being separated at infinite distance but surrounded by water molecules, no big deal, right? You're replacing an electrostatic interaction between two ions with many ion-dipole interactions with many other water molecules. And that's a general theme throughout non-covalent interactions. Their strength is going to depend on context. So I'll give you some other examples of that as we talk about other non-covalent interactions. Let's start today with hydrogen bonding. Hydrogen bonding is really a kind of dipole-dipole interaction. Your text, I think, talks about it in its own special category, in part because hydrogen bonding is stronger than, in many cases, other dipole-dipole interactions. Nevertheless, it comes from what you expect for a dipole-dipole interaction, that is, oxygen's more electronegative than hydrogen, so we should have a partial negative charge on oxygen and a partial positive charge on hydrogen. Dipoles are vector quantities, so we could draw an overall molecular dipole like that. And doing that is an example of why something like water is polar, whereas carbon tetrachloride is not. In the case of carbon tetrachloride, chloride is more electronegative than carbon, and you have these individual bond dipoles that all cancel each other out, and so the vector sum is 0. That's not the case with water, and water molecules can interact with each other. Usually in liquid water, both lone pairs of the oxygen are involved in hydrogen bonds with other water molecules. Though these hydrogen bonds are transient, meaning they are short-lived and they rapidly exchange, meaning I've drawn this water molecule as though lone pairs on this oxygen were hydrogen bonding with a hydrogen from the other water molecule, but this hydrogen bond could be easily replaced by a hydrogen bond with some other water molecule. It's in rapid flux. And so there's a fair amount of disorder or entropy. Of course, if you lower the temperature, you can freeze out literally some hydrogen bond networks of water in sort of tetrahedral type patterns that form hexagons and are related to the beautiful shapes of snowflakes. I want to talk a bit more about what I mean by transient and short-lived. In water, it's very easy for water molecules to trade protons with each other. I'm not sure what I just done there, sorry. And actually what I was going to talk about, I want to do something else first, so I apologize for that. Terrible segue. Hydrogen bonds have partial covalent character. Some hydrogen bonds can be as strong as 10 to 15 kilocalories per mole, which is still only about 10% of how strong oxygen-hydrogen sigma bond is. Although we've formulated hydrogen bonds as being just interactions between complementary ends of a dipole, you can think of it in terms of sort of a HOMO-LUMO interaction. The HOMO of a water molecule is non-bonding lone pair on the oxygen, which we could show in some kind of atomic orbital. The LUMO of water is one of the two oxygen-hydrogen sigma star orbitals, which should have a node in the middle, a lobe on the hydrogen and a part on the oxygen. And in part, you can think of a hydrogen bond as partial, not complete, but partial mixing of the lone pair orbital on one molecule with the oxygen-hydrogen sigma star on another. Okay? And you can imagine sort of a limiting case where one water molecule might completely mix with the oxygen-hydrogen sigma star. And if that happened, that would just be an acid-base reaction, right? That would just be generating H3O plus and OH minus. And, you know, in 55 molar water that is neutral, pH 7, you've got about 10 to the minus 7 molar H3O plus and about 10 to the minus 7 molar OH minus. And so, not a lot, but 10 to the minus 7 molar is still a heck of a lot of individual molecules. So it happens at some rate. What I mean to say is it's actually very quick for water molecules to trade protons, right? Struggling to figure out how to do this. So let's just, no, I didn't want to do it that way. I'm going to show a chain of hydrogen-bound water molecules. And I'm not really caring how many water molecules are in this chain. This is just for the sake of an example. Imagine that we could label one of these hydrogens with some technology. So let's figure out, we figured out some way to stamp that hydrogen with a star or something like that. Actually, we have. It's called isotopic labeling, but we don't need to worry about that. It's pretty easy for lone pairs on this oxygen to reach over and steal that proton, and then to reach over and steal that one, and that one, and that one, and that one. And pretty soon, everybody just traded hydrogens. It's like a bad soap opera. It's very easy for some of these bonds, which used to be covalent, to now just become hydrogen bound, and other bonds which used to be hydrogen bound to become fully covalent. See what we did there? We sort of traded. Everybody took a hydrogen from the left and passed one down to the right. It's like a Christmas game we sometimes play at our house called Tommy Wright. The kids love it. It's predictable. It's kind of stupid, but we all have a mystery candy bar, and then you read this story, and every time it says right, you pass the candy bar to the right, and then when it says left, you pass the candy bar to the left, and if you can tell that you got the Kit Kat, but then you have to pass it to the left, you get angry and punch somebody. Lots of fun. But water molecules are rapidly trading hydrogens in this way. It's called proton exchange. And what this means is if you took a single extra proton or a single extra molecule of H3O plus and you dropped it in a beaker of water, the H3O plus that you put in there no longer has that proton. And the proton is just somewhere, and it's extra and shared among lots of multiple water molecules. So what you need to remember about hydrogen bonding in water is it's transient, it's short-lived, rapidly exchanging, lots of disorder, though it is strong enough for some interesting phenomena to be observed. For example, the surface tension of water derives from hydrogen bonding. Okay? Hydrogen bonding shows up in biology in lots of different places. If you've learned anything about proteins, you maybe have heard of something called an alpha helix. Familiar to anybody, vaguely? The alpha helix involves the protein main chain, which we're not going to learn about really until 352. And there are side chain groups sticking out at various points along the helix, but you've got this spiral pattern among the main chain. And individual levels of the helix, if we zoom in on them, what we see are carbonyl oxygens from the amide bonds in the back in the protein. I didn't do this last time, and I need to. These little pink squiggly marks indicate there is other stuff here I'm not drawing. And instead of writing that out every time, I'm just using the pink squiggly line. Is that okay? Sometimes I'll forget to make it pink. But you've got carbonyl oxygens on one level of the helix, hydrogen bonding with amide protons on the other level of the helix, and so on and so forth all the way down the helix at various positions, wrapping all the way down. And it's thought that these hydrogen bonds at least provide the specificity or instructions for making the helix. And it's also thought that they contribute to the stability of the helix. In other words, they make it okay for the protein chain to adopt this ordered structure that's a spiral instead of some more disordered structure. The issue is controversial, though, because if you think of an unfolded protein, we typically envision these as being just an extended, spaced out, no regular structure or shape. But those carbonyl oxygen and amide proton groups are still going to be in the unfolded protein, and in this case, instead of hydrogen bonding with each other, they're going to be hydrogen bonding with water. And so the real question that people have asked is, how much do these hydrogen bonds contribute to the stability of this helix when you can easily replace them in the unfolded protein with just water? And this is an interesting issue that people have argued over through the years. It's thought that for many proteins, actually, they only form helices after they've done something else that provides the real driving force for folding. We'll actually talk about that a little later today. It's called the hydrophobic effect. I won't draw the examples of hydrogen bonding in DNA. Presumably you've seen the nucleobases A with T and G with C before. If you haven't, it's worth going looking up. But I want to spend, I think, the rest of our time today talking about another kind of non-covalent interaction called van der Waals interactions. But any questions, anything anybody wants to ask about hydrogen bonding?
Yeah, so with the coiled one versus the uncoiled one, the uncoiled one has more surface area, right? So is that a bigger factor than hydrogen bonding when we talk about boiling point stuff?
Yeah, so the unfolded protein might have more surface area than the folded one, especially if that unfolded protein exposes nonpolar groups to water. That's a problem. And so in many cases, we'll talk about this, but sequestering nonpolar groups out of water is energetically favorable, and it actually drives formation of protein structure in many cases. Yeah?
What would be the types of questions that you could ask us about this?
What would be the types of questions that I could ask you about this? How do I answer that without confirming whether or not I have asked a question about this? Well, it's always possible for me to ask you why something occurs and then give you some options to choose from. That's as I think about questions, I have written about this section of the material. Most of them are sort of, here's a situation, an observation, explain why it's this way based on what you know, and then you've got some options to choose from. Somebody has asked whether or not the exam will be open internet. Will I clarify? Yes. So the only thing Proctorio is going to do is it's going to prevent you from right-clicking on the test images so that to protect you from the temptation to right-click and post them and get help from some other human. You may use the internet. You may use Google to search for things. You can use your online text. All of that's fine, but your work has to be your own. So, as I've said, the only other intelligence that you can use besides your own is the Holy Ghost. We're not counting Google as an artificial intelligence. You are welcome to ask questions into the Google. Just beware of the answers, because who knows where they come from. All right. Study guides are okay. If you've never used Proctorio before, I think you'll need to take the exam using Google Chrome, and it will prompt you to download an extension from Proctorio, which should work. If you have trouble with it, let me know. All right. Book is okay. Yep. Nobody believes this. Is it really true? Yes. The policy on this is because I know that I don't want to penalize the vast majority of people who would, in good faith, actually take a closed book exam at home properly, on the off chance that there's a few people who wouldn't and they would feel like they had an unfair advantage or something like that. So, yep. Everything is okay except for Chegg. Yes, and or FaceTiming with your grandma. I'm not sure how much help she'd be, but she can't. Don't ask her for help. All right. But feel free to try to explain some of this stuff to Grandma. I've always thought that if you can explain it to a non-expert, you really understand it. Go ahead.
Could we go back to, so you can think of H bonding as a homo-lumo interaction.
Yeah.
And you can think of H bonding as it's kind of overlapping, but if it fully overlaps, that could just be an acid-base reaction.
Exactly. So there's this continuum. Yeah, the question was, if we think about hydrogen bonding as a homo-lumo interaction, we think about partial mixing, partial sharing. But if you go too far, it's just an acid-base reaction proton transfer. There's actually a continuum between full-on proton transfer acid-base versus hydrogen bonding, and it gets kind of mixed up. There's a particular class of enzymes called the serine proteases or lipases, and they involve a catalytic triad where there's a single proton that's shared pretty much evenly between two groups, and it's unclear who's covalently bound to whom. It's just sort of in between sharing. So yeah. Anything else? Yeah, go ahead.
So when we talk about PKAs in a couple lectures ago, we talked about which side it favors. You can have a situation where it's like 16, 16 and a half. Is that the kind of concept we're talking about, or is some won't be fully post-COVID?
Oh.
Spectrum?
Okay, so the question was asked that when we talked about acid-base stuff, we had situations where we looked at some equilibrium and we said, well, what if the pKa's on either side, if we identify the acids, what if they're basically the same? What that means is at equilibrium, you would expect equilibrium constant to equal 1, meaning, I guess, technically that this product equals that product. That doesn't mean that a proton is 50% shared between the two. It means, on average, you've got 50% this and 50% that. However, the situation that we just talked about, where we've got homo-lumo sharing, and a proton might even be sort of shared evenly in between two groups, that works best when the pKa's of either group are just the same. Yeah. Okay. There's this whole area of physical organic chemistry that plots the energy of an interaction between protons and those two groups as radius between the two groups, and the proton, if it's too close to one, energy goes up, and if it's too close to the other, energy goes up. There's a barrier to go from one to the other, and if that barrier gets low enough, you can actually tunnel across it. It's all exciting and complicated, but now I've scared you, so I'm going to back off, and we won't worry about that. All right. All right, so I wanted to talk about van der Waals interactions. These are dipole-dipole interactions. I'm sorry, I said that wrong because I get it wrong every time. Induced dipole interactions. Induced dipole interactions. These, what do we mean by that? It's kind of confusing. So we're going to start with some long chain hydrocarbon. And we're going to draw at least some of the carbon-hydrogen bonds. And we're going to think about the distribution of electron density in this molecule. This is why we don't normally draw all the carbon-hydrogen bonds, because it takes forever. If we had this molecule alone in the gas phase, let's just, I don't know. Let's just draw the electron cloud that would sort of surround this molecule. And we're going to color everything gray here because the distribution of electron density in this molecule should be uniform in the gas phase. Carbon and hydrogen have similar electronegativity, so we don't expect any permanent dipoles here. We don't expect one part of the molecule to have a concentration of positive charge and the other part of the molecule to have a concentration of negative charge, which would be the case in a molecule like ethanol or water, where there are large electronegativity differences and where you can draw permanent dipoles. So on its own, the molecule's just sort of meh, an even distribution of electron density. If you imagine bringing two of these molecules together to fairly close distances, if you got too close, the electrons would start to repel each other. And so that actually defines what's called the van der Waals radius of various atoms. It's when the repulsion between the electrons starts to take off and the atoms can't get any closer to each other. But a little bit just shy of that distance, before repulsion really takes hold, what can happen is that the molecule can temporarily reorient its electron density such that it can be temporarily positive along this face. We'll use blue for positive, and temporarily negative along this face. So partial negatives up here, partial positives down here. Now this is not permanent. It's in flux, and it could switch from one moment to the other, but it happens, and it's strong enough when it does that it can hold two of these molecules together if you've got enough of this going on. So temporary, transient, non-symmetrical distribution of electron density. All right? And of course, the next moment it might switch, and everything that was blue in this moment might be red the next moment. But even though it's switching back and forth, the net effect is that the two molecules are attracted to each other at some level. Now, it's very short range. It tends to fall off as 1 over r to the 6th. And it tends to be, the strength of this interaction tends to depend on two things, all right? One is contact surface area, and the other is polarizability. Polarizability is related to how easy it is for a molecule to temporarily distort its electron density from being uniform. So we'll see that molecules, well, we can use van der Waals interactions to explain a lot of trends in organic chemistry. Your text makes a pretty big deal out of physical properties, melting point and boiling point. I really don't do that in the class. It's possible you'll encounter that in the future on the MCAT or the DAT. But I do want you to understand these two principles. So I want to start with polarizability because it's maybe a little bit easier to understand. We're going to compare fluorine gas, F2, with Cl gas, Cl2, versus bromine versus iodide, okay? Fluorine is a gas, chlorine is a gas, bromine is a liquid, a red liquid, and iodine is a purple solid. We're not worried about the colors, but the physical state, at room temperature anyway, is instructive. Now, these molecules are not polar, right? Even though fluorine's electronegative is all get out, when it's bonded to itself, there's no dipole. So polarity is not an issue in explaining why iodine is a gas and fluorine is a gas and iodine is a solid. What is the difference? If it's not due to polarity, it maybe needs to be due to van der Waals interactions. The solid should have stronger van der Waals, VDW, interactions because the stronger interactions are between molecules, the more energy you have to put in to break those interactions, the more temperature, the higher the temperature needs to be before the solid melts. It's an aside, but it's a useful way of thinking about temperature in organic chemistry. You can think of temperature as the average kinetic energy of the molecules that you have in solution. And in a lot of cases, translational kinetic energy, their speed and bumping into each other. If the van der Waals interactions are strong, you have to apply more energy to break the interactions to give each molecule enough kinetic energy to be moving around. So why would the van der Waals interactions be weaker for fluorine than for iodine? We already know that iodide is bigger than fluoride, right? Hannah, you were raising your hand. You're about to say something, no? No. Okay. Sorry. Forgive me for calling you out. I didn't mean to anything by it. The issue is polarizability. Iodine is large. Its valence electrons are held far from the nucleus. They don't feel the nucleus quite as much because of the shielding of the many levels of core electrons. And what this means is it's fairly easy for iodine to distort its electron density, moving the electrons to one side or to the other. In the case of fluorine, fluorine is small, the electrons are tightly held, and therefore it's more difficult to move the electrons to one side or the other. Iodine is more polarizable, and what that means is it can muster a larger negative face on one side and a larger positive face on the other, and so iodine molecules stick together better. Yeah?
Sorry, I have some questions.
Yeah.
Would it also give you a surface area because it's a larger molecule, or is it just so insignificant of a difference?
Could it also be surface area? Certainly, though the issue is not necessarily surface area per se, but how much surface area you can get in contact. So all of these molecules have similar shape, so I'm not sure if there's a difference in how close they can get to each other. That's actually a good question. I don't know. Yeah?
So, correct me if I'm wrong, but is that molecule more polarizable at iodine? Because like there's a bigger like electron cloud, like more space for the electrons to move around.
Yes. Yeah. So the question is, does the greater polarizability of iodine have to do with its size because the electrons are spread out over a larger area? There's more space to move around. Yeah. Yep. Good. That's a good way of thinking about it. Much larger electron cloud for iodine than for fluorine. Okay. So I want to talk about contact surface area, and the most interesting way I think to illustrate this is to talk about something that's controversial in the food and diet industry, and that is fats. When I was little, in the 80s and early 90s, 10, 12, 14, 16, there was a tendency among the people recommending various food lifestyles to demonize fats. And as a result, this whole cottage industry of low and non-fat foods broke out, and you could go to the store and get this little box full of cookies that had 0 grams of fat, all kinds of sugar, like crazy amounts of sugar, but we thought, hey, carbohydrates are great, sugar is great, that's fine. It's fats you really want to avoid. And so we ate to our heart's content and then discovered that that was a problem. And so now understanding has evolved that there are some kinds of fats that are not as bad as others. And so we're going to talk a little bit about their structures. What I've drawn for you here is called a triacylglycerol. Glycerol is this portion of the molecule. Glycerol is an alcohol that has 3 OH groups attached to each of 3 carbons. And then this part of the molecule is called an acyl group, but if you break the ester into an alcohol and a carboxylic acid, what you have is a fatty acid. You've maybe heard about different kinds of fatty acids before. These are the long nonpolar chains associated with fats versus oils. What is the difference between fats versus oils? Anybody know? Physical properties, what do you observe for fats versus oils? Oils are liquid at room temperature. All kinds of oils, right? And fats, solid. You can tell that because if you go buy some Crisco or shortening, it's this opaque white solid. My favorite example of fats was when I was on my mission in the Rio Grande Valley of Texas, and we would go to, I learned Spanish, but only the kind of Spanish to teach the gospel. The rest of Spanish that I learned was sort of a mix of whatever we could say. So we talked about going to La H-E-B, which was the store. I don't know if any of you are Texans, but H-E-B is a grocery store in Texas. They have these big buckets. I can still see them. Big yellow buckets, five-gallon buckets of manteca, which is lard. And you'd use those to make tamales, and it's really good if you use the real stuff. Tamales are great when, you can tell they're great when they leave this sort of red grease that makes the paper plate beneath it translucent, see-through. That's a really good tamale. Anyway, lunchtime yet? I should have some tamales. Where were we? Yes, fats are solid, oils are liquid, and the reason has to do with the structure of the fatty acid chain. All right? Now, most of these fatty acid chains are anywhere between 12 and 20 carbons long. Fats are solid because they have mostly no double bonds. And we call double bonds degrees of unsaturation. Molecules without double bonds, each carbon is fully saturated with carbon-hydrogen bonds. That's where the term comes from. So we call these saturated fatty acids, and the fats that come from them are called saturated fats. So I'll just give you an example of the physical properties of some of these saturated fatty acids. I'm talking about a carboxylic acid with a long chain, nonpolar chain, and we'll talk about numbers of carbons in that chain, and then we'll compare melting points. Clearly, I don't intend for you to memorize numbers, so just we'll think about the trends here and what we can learn from the trends. So 12, 16, 18, 20 melting points, 43, 63, 69, and 77. So all melting points, even 12 carbons long, well above room temperature. Solid, like the lard in the bucket. Why do you suppose the melting point increases as we add more carbons? Based on what you know from van der Waals interactions.
There's more area that's connecting the molecules together.
Right. The more carbons you have in a chain, the more surface area the molecule has, the more opportunities for close interactions between the molecules that generate these induced dipoles. Okay? So this is an example of increased surface area. Oops, there we go. Increased surface area leading to increased van der Waals interaction strength, leading to increased melting point. All right? And boiling point as well. Your text makes some subtle differences between melting point and boiling point and crystalline structure and compactness. We're really not going to go there, just because I don't want to, not because it's not important to some people. In contrast, let's look at the unsaturated fatty acids. I'm going to list number of carbons here, and then I'm going to list here I'm going to list here the location and configuration of double bonds, and then we'll list melting point here. Unsaturated fatty acids have one or more double bonds in it. If it's a monounsaturated fatty acid of the kind that's found in a lot of different nuts, it's got one double bond. If it's polyunsaturated, it's got multiple double bonds. 16 carbons with a cis or Z double bond starting with carbon 9 has a melting point of 0. Compare that to 63 for the fully saturated one. That's an enormous difference, right? This would be liquid even outside on a fairly brisk spring morning. I guess that's not surprising. I don't know. 0 degrees Celsius, freezing point of water. Let's talk about why. So let's draw the 16 carbon chain that has no double bonds in it. 2, 4, 6, 8, 10, 12, 14, 16. And then let's draw the one that has the cis double bond. 2, 4, 6, 8. This is 9 to 10 is a cis double bond. 11, 12, 13, 14, 15, 16. Close enough. Now that's a dramatic change, so something must have changed in terms of the van der Waals forces here. What do you think it is? Okay, somebody on the chat is chiming in more surface area, although that was an answer to a previous question, so silly. But it's true here as well. But not in terms of total surface area, because that's got to be about the same for both of these molecules. They have similar numbers of carbons. What else could it be? Go ahead.
So I think what it's trying to do is
Okay. Yeah, it has to do with shape, right? The answer here in class for those of you following along at home was just that the cis double bond in the unsaturated fatty acid creates a shape that, first of all, you can't rotate around double bonds for reasons we've already talked about. And because of that restricted rotation, the two chains with the double bonds can't approach each other quite as closely. They don't have the flexibility to accommodate each other and adjust each of their shapes to maximize surface area. The kink in the chain makes it more difficult to pack these molecules together. The analogy is if you have pieces of wood 2x4 that are very straight and not warped, they stack nicely. But if they're warped and twisted, they don't stack as well. The contact between each individual board is not as good. And therefore, because we have lower contact surface area here for the unsaturated fatty acid due to shape, we have weaker van der Waals interactions, and therefore we have a lower melting point. And the same would be true for boiling point. And in fact, you can introduce even more carbons. Let's see, I'll skip the 18 one. If you introduce 4 double bonds into this chain that's 20 carbons long, recall that when we did that for the saturated fatty acid, melting point was 77. We've got 4 double bonds in there, melting point is minus 50. Okay, so the more double bonds you have, the more the weaker the van der Waals interactions are, and therefore the lower your melting point is. And this has a consequence in terms of the physical properties we observe. All right. So want to spend the last little bit talking about water solubility of these molecules, because our ancestors discovered that you could take these fatty acids that you would get from rendering animal fat in lye, and you would come out with the potassium salt of the carboxylate, and they found that this would make soap. And the reason they found it would, there's a beautiful chemical reason for why they found it would make soap. This molecule has a polar head group that can interact easily with water. It can hydrogen bond with water molecules. It can participate in transient, short-lived hydrogen bonding. It fits in nicely with water molecules and doesn't disturb them. But it's got this nonpolar tail that has trouble with water. You know that oil isn't soluble in water, that long hydrocarbon molecules aren't soluble in water, but you may not know why. You may have been told or may have thought that it's because the van der Waals interactions between the oil molecules are so strong that they can't be broken apart by water. And that's actually not true. Van der Waals interactions are pretty weak, and water can engage in them as well. The difference has to do with what happens to water when a nonpolar molecule is in it. So recall at the beginning of the lecture we told you that water was this rapidly fluctuating network of hydrogen-bound water molecules with lots of hydrogen bonds but also lots of disorder. When we put a nonpolar molecule in water, what happens, because the nonpolar molecule cannot hydrogen bond with water, the water molecules around that nonpolar molecule have to go out of their way to accommodate that nonpolar molecule. They can't hydrogen bond with it, and so they maintain this ice-like network of water molecules in the immediate vicinity of our nonpolar group. And I think, if it's okay, I'm just going to indicate that with this sort of blue circle. Now remember, I told you that each water molecule in regular water doesn't contain any nonpolar groups. I'm sorry, I hate that. I don't know why we did it that way. Now we're erasing things. Bloop, 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 bloop. All right, whatever. In regular water, each water molecule, each lone pair can participate in 2 other hydrogen bonds. Now that we're surrounding a nonpolar molecule, some of the lone pairs of oxygen just aren't in the right spot to get another water molecule. So we lose some hydrogen bonding, which should be unfavorable. We lose some interaction strength. I'm just trying to move that over, but I can't. In addition, the water molecules, in order to sort of compensate for the lost interactions, strengthen the remaining hydrogen bonds and get closer to each other. And that causes them to lose a large amount of entropy. This is a rigid, ice-like cage of water molecules that surrounds the nonpolar groups, right? So if you think about this in terms of free energy and whether a process is favorable, imagine water before putting something nonpolar in it and water afterwards. Before, the water molecules have maximum ability to hydrogen bond and they have a lot of disorder. Afterwards, some of the water molecules have lost a lot of entropy to form this hydrogen-bound shell around the nonpolar molecule, and they've lost a good number of hydrogen bonds as well. And so remembering that delta G equals delta H minus T delta S, if our entropy increases because we've lost hydrogen bonds, and if our entropy decreases because we've lost disorder, overall the process should be unfavorable. So it's unfavorable to put nonpolar things in water. Not because nonpolar things like to stick to each other, but because doing so reduces the entropy of water. Similarly, if we look at it the other way, if we have something nonpolar in water, it's favorable to take the nonpolar thing out of water and to bury it. All right? So this has an impact on how we use nonpolar molecules. For example, the nonpolar molecule fatty acid we've looked at here has a polar head group and a nonpolar tail. Its shape is roughly conical, and because of this entropy effect that we've talked about, individual fatty acid molecules will self-assemble into spheres where the surface of the sphere is the nonpolar head groups, and the interior of the sphere is the polar head groups are on the surface and the nonpolar tails are in the interior, and this is a supramolecular structure called a micelle. It works as soap because grease can be in the middle with the nonpolar tails, and yet the whole thing is soluble in water. In contrast, there's another class of molecules called phospholipids, where you have a polar head group attached to one of the oxygens of glycerol, and then you have nonpolar tails attached to the other carbons of other oxygens of glycerol. And if you've taken a biology class, they've probably represented this to you as a phospholipid with a circle on top and 2 tails. The shape here is cylindrical, and so what happens is these will self-assemble not into spheres, but into leaflets where the nonpolar groups can be side to side. If we stopped there, they would still be exposed to water. So the 2 leaflets will come together, and there is your lipid bilayer. And the driving force for forming that is sequestering those nonpolar tails from water so that water can have maximum entropy. All right. So this is the foundation of forming membranes, which is really what separates things that are alive from things that are not, and really important to life. One thing your text does point out that I think is useful to know is that in terms of determining how nonpolar something can be before it gets not soluble in water, the rule of thumb is for every 5 carbons, you need 1 hydrogen bond donating group. That means 1 bond between an electronegative element and hydrogen. And in general, if you've got that, you're soluble. If you have less than that, you're not. So ethanol is freely miscible with water. People drink it all the time. In contrast, octanol is not soluble in water. And it has to do with the number of carbons we have per hydrogen bonding group. All right, sorry about that. That is it for today. That will take us through the end of the exam. Good luck, and we'll see you next time.